Okay, let's see.
It says that it's streaming.
Okay. Okay. Right. Well, fantastic. Good afternoon. We made it. Good afternoon, guys.
It says that it's streaming.
Yes, we are live. Welcome. Welcome to the February event of Astronomy on Tap Jena. And I will close all the other noises, but hopefully you will hear me. Okay, so let me introduce myself and then the fantastic guest we have today with us. So I am Eleni Vardoulaki. I'm a postdoc researcher at the Tautenburg Institute and also the founder of Astronomy on Tap Jena. And today we have with us Dr Sümeyye Surí, who did her undergrad in the Ankara University, the Astronomy and Space Sciences. And then she moved to Bonn with a Bonn-Cologne Graduate School scholarship. I was also in Bonn before.
Yeah, that's where we met.
And I miss it very much. She did her master's in Bonn and the PhD in Cologne. Yeah. And now she is a postdoc at the MPIA in Heidelberg, where she studies the structures of molecular clouds and specifically filaments. She will tell us more about that. Yeah. And how high mass stars form. And she uses interferometric observations. She will also tell us a bit more about that. Yeah. And one more detail is that she's the creator of the amazing podcast, iAcademic. And you can find it on Spotify and Apple. What is it?
Google? Apple Podcasts.
Podcast. Okay, Apple Podcasts. Yeah, you will tell us all about that. It's exciting. Welcome. So I will have some background noises, guys, but you know, working mother. So our second guest is Dr. Eike Guenther. Dr. Guenther is a research scientist, a staff scientist at Thüringer Landessternwarte Tautenburg.
Good.
I said it, yes. My German is getting better. And he's an expert in exoplanets, which is amazing. It's very exciting. And also he's very active in public outreach. And he will appear in a TV series here in Germany. And I really
yes.
Oh, wow. I want to know more about that.
Actually, yes, because of the public outreach, and I'm always the first person to the media. There will be actually two things. One is a movie, which was supposed to be shown last year in the cinema. And they invited they showed 5 slightly strange persons or with strange professions and made a movie out of it. And we set already the date in Berlin in the cinema with all the 5 people there. And then, of course, the COVID came and we couldn't do it. And the name of the movie is The Perfect Black. And we should speak about this. And so I hope that this movie comes out next year. And then we had this TV series in aller Freundschaft, which is a kind of soap opera, which was filmed in Tautenburg, and I play a little role in the happy end in the end.
Okay, you will tell us in a bit. I will start with a show. So we have an icebreaker for you, for Sue and Ike. So, you know, they break a bit the ice. And let me share my screen to explain what's going to happen. Right. So
okay.
This is our event today. We have a lot of games. So first game is an icebreaker. We play taboo. And you have to describe a word. This is not a word you need to describe, but so I will give you a word privately on the chat. And then you will have to describe it to the other person without using the 4 words underneath. Okay, so you have to describe universe without using all the other words. Do we have it? Okay, good. I will stop sharing now, and hopefully this will work. So,
but
yes,
are we doing this together or in sequence? Or?
Yes. So first, Sue will describe this word to Ike. Okay. Wait a minute.
Okay. You're sending it only to me.
Only
Right?
to you. Only
Yes,
to
and
you.
I have to guess what it is.
Yes, yes.
Okay.
So the first word inside the brackets is the one you need to describe, and then you cannot say any of the others.
Ooh, okay.
Mm.
So this is similar to the kind of object that we live.
Planet.
But far away.
Similar to the kind of object we galaxy?
Smaller scale.
Ah,
The first thing you guessed was correct, but
yes, what was then spiral arm?
no, much smaller.
Solar system.
Still smaller.
Earth moon system.
Basically, the kind of object on which we live.
Yes, the Earth, a planet.
Yes, but not nearby. So.
Moon.
Outside of our immediate circle, around probably a different object that also does hydrogen fusion.
Sun.
No, so so
we're almost out of time. One more attempt.
Or Jupiter? No, Jupiter doesn't do fusion reaction. So Sun. Or do you mean fusion reactor?
No, so the type of object that we live on that you guessed correctly.
Yes.
But
planet.
On the orbit.
Rocky planet.
Of a different different sun.
Exoplanet.
There we go.
Oh, okay.
Okay, it was difficult because she could not say planet, orbit, star, or system.
Okay.
So I made it extremely difficult.
Oh, now I get a difficult one.
Okay, hopefully the next one is easier. So Ike, this is for you to explain to Sue.
And I click onto the chat, or where do I click?
Yeah, to the chat. It will appear only for you. You have to describe the first word inside the quotes, and you cannot say the other four. You have to describe the first one. You cannot say it.
Okay, this is the thing in the Earth atmosphere, and when it lights, it's either snows out of it or it rains out of it, and it contains water. And it's in the Earth atmosphere.
Cloud?
And sorry?
Yes.
Cloud?
Yes.
Cloud.
Eleni, you were thinking of a different cloud, but then I thought cloud is cloud.
Her expertise in molecular clouds. So I should have put
but the word here is cloud, and you say I cannot say star formation, cold, or molecular, and so I use
yes.
different.
I made it too astrophysical. I should have put it closer to Earth. But good, fantastic. You guys rock. Okay, so one more round. So this one is for Sue to explain to Ike.
Okay. Livable.
Livable.
For again, like when we talk about exoplanets.
Yes.
Yeah.
Habitable zone.
There we go.
Yay! Yes, very nice. Okay. I'm sorry.
Now I have to click again.
My son is doing the monkey today, climbing up doors. Okay, so this is for you, Ike, to explain, to describe to Sue. And that's the last one.
Okay. So system in which we live, at the same time also a chocolate thing with coconut inside that you can eat. It's the same word. And we orbit around this thing in
Milky Way?
I can use this. We orbit around this.
Yes,
Sorry?
Milky Way. Yes.
Exactly.
Yes.
Milky Way.
You guys rock. So this was the icebreaker. Congratulations. You did a great job. Fantastic. I didn't even have to use my extra word. And now, hopefully without interruption from the little monster, we will go to our interview. Before we go to our interview with Sue, guys, I don't have someone in the chat today to interact with you. I will try to interact when I have time. Write where you're from. Tell us your thoughts. Give us feedback if you like it or not. We will play more games. We will have 2 interviews, and there's going to be a quiz. The quiz winner will win a private session with me to explain astronomy. So I can answer all your astronomy-related questions. Okay, so we will Zoom together.
And what shall we do?
At the moment, you can also play, but not yet. Now.
Okay.
Now
So we now I drink just tea.
Now you can relax, and I will talk a bit with Sue and find out what has been up to all this time. Sue, I'm very happy to have you here. You've been very active in astronomy and outreach, and I really want to learn more about it and for our audience to learn more about. So can you please start by telling us a bit about your education and expertise and what inspired you to get into astronomy?
Sure. Yeah, as you mentioned in the beginning, I'm from Turkey and I did my undergrad in the capital of Turkey at Ankara University. And I studied astronomy and space sciences. Then I moved to Bonn to do my master's, then moved to Cologne to do my PhD, and now I'm in Heidelberg as a postdoctoral researcher. What inspired me to go into astronomy was, I guess, the biggest reason is the Turkish educational system, which did not allow me to study chemistry.
Okay.
No, but all jokes aside, I as a kid I loved my favorite thing to do was investigate things under my uncle's microscope that he would let me play with, and that was just yeah, so much fun, and I feel like that made me kind of want to do science, and and I also feel like astronomers are the kids who never actually stopped asking, but why? And I'm one of those kids, and I feel like astronomy is one of the branches that really satisfy that curiosity in me in my everyday life.
Yes, I was okay. I was psyched when you said that the Turkish education system drove you to astronomy. Because if I compare to the Greek education system, it would drive me away from astronomy. Because they took away astronomy from schools now. So when I was a student, they had a class at school. They didn't care so much about it. The teachers didn't care so much about it. Now they removed it completely.
Okay.
So not so cool. But it's great that this path drove you here, because what you study, molecular clouds and what happens inside galaxies has to do a lot with chemistry, no?
Yeah.
Is this why you chose this field? You liked?
Yeah. Yeah, this is exactly what happened. I wanted to do chemistry so much, but yeah, I didn't get into a chemistry department. But then while I was doing astronomy, I realized that I could do astrochemistry, and that kind of also initiated my transfer from Bonn to Cologne, because people in Cologne did more astrochemistry on smaller scales. And then I ended up doing star formation, which is not really astrochemistry, but we still, work with molecules and everything, and it's fun. Yeah.
So tell us a bit more about what happens inside the clouds and galaxies, and
Okay.
all this chemistry and how we can observe them and study them. You know, a
Yeah.
bit of background on what you do.
Okay. Yeah, so we've been talking about molecular clouds, but for the broader audience, the space between the stars in our galaxy is not empty. And in fact, it's filled with, you know, gas and dust and magnetic fields and radiation and all kinds of stuff. And my work, and you know, most of my interest focuses on a certain constituent of this space between the stars, which we call the interstellar medium. And this constituent is the molecular clouds, where we can find really cold and dense gas, and this is where the stars form. And my work basically focuses on the structure of molecular clouds, which very recently was discovered to be filamentary. And if you don't know or cannot imagine what a filament is, imagine these neural networks or the cosmic web simulations maybe many people have seen, where material or information is transported along these elongated objects. And for a long time in observational astronomy and in theoretical astronomy, people thought that, you know, molecular clouds were these like giant balls of gas and dust. But for the past decade or so, it is clear to us that all molecular clouds are composed of filamentary networks where accretion happens, where collapse happens, you know, which eventually leads to the formation of new stars. And
so this is where new stars will be formed, right?
Yeah,
and
yeah.
Accretion is when material goes around and around. I'm saying it very, very simple.
Exactly.
For the non-astronomers in the audience.
Yeah.
And these filaments could be like strings, right?
These filaments are basically like strings. Yeah. So filaments are basically over-dense regions that are elongated, so longer than their width. Yeah, basically stars form along the overdensities. You can imagine them as knots of gas along these filaments. And sometimes we see that when filaments merge, so at the densest points of these networks, we see clusters of stars forming, because material can be pulled towards these dense clusters along the filaments, and then you can have enough gas to actually form multiples of stars.
Okay, that's very interesting. And so how is the chemistry around there? Because you were interested in chemistry. So how about the chemistry in these regions?
So I should admit that I don't do much chemistry, although I have been in working groups that did chemistry. So most of my knowledge about astrochemistry is not coming from the work that I do. But sorry, this is a special appearance from my cat.
Very cute.
So basically, the chemistry is we have a lot of hydrogen and helium. But as the name says, these are molecular clouds, and these are the places where we can have densities to form molecules such as carbon monoxide, which is the one that is observed most easily because it radiates at these very cold temperatures that are around 10 kelvins. We can have, so once, for example, a star starts to form and it starts to create chemical reactions surrounding it, we can have, for example, molecules that has sulfur. We can have molecules that have nitrogen and oxygen, and yeah, and ions too.
Wow. And how do we, sorry, how do we observe this from the Earth?
So basically, because these are very low energy transitions, we're able to observe them in longer wavelengths, which means that we use radio telescopes or infrared telescopes, either far infrared or mid-infrared, to basically disentangle the structure of these objects.
Okay. That sounds very interesting. And is this what you do in your research, or?
Yeah. Yeah, that's what I do. I have not been able to travel for the past year, just I guess like the rest of the world.
Yes. So
but
what do you usually do? Where do you go?
I go from my bedroom to the living room where my desk is.
Sorry, my son is showing me our live feed, and he's going thumbs up. Thank
Thanks,
you.
Iris.
And he subscribed. He subscribed to us.
And all notifications.
Okay, so now we're famous to the young generation. But so usually, if we didn't have this pandemic that we're living, and we cannot move from place to place if it's not, within 10 meters. Where would you go? Which telescopes do you visit? And do you collect data yourself?
Yeah, so this is actually my absolute favorite part of what I do, is going observing, because by traveling to different places, such as where the telescopes are, such as, Spain or different parts of the US, I not only get to eat a lot of good food in these places, but also kind of, learn about like the technical parts of, how we actually get the data in our laptops, which is fun. And sometimes I'm allowed to use the telescopes to observe my own project, and that's a lot of fun. Just to, it's one of the things that motivates you as a kid or as a teenager, just looking at these watching these movies where people sit in control rooms and like operate telescopes, or count down to whatever space event or something like this. It really makes you feel like that, and I think that's one of the fabulous parts of what I do.
Yeah, I think that's amazing, and
Yeah.
a lot of observational astronomers enjoy that part the most.
Yeah.
So we don't really enjoy staying at home and doing Zoom meetings all day. Yeah. And also we don't enjoy now that astronomy is changing and you have your data being collected for you.
Yeah.
So you don't get to go to the telescopes anymore, but you have resident astronomers, so astronomers that live there, they work there, and they observe your targets and send you the data. So the ones that had the opportunity to actually collect their own data and operate a telescope are very lucky.
Yeah, I've been very lucky to go on many observing trips and operate telescopes, and it is true that we don't get to do that anymore because the observatories are getting more and more expensive, and this basically allows for very little room for mistakes.
Yes. Why? We don't make mistakes. What are you talking about? But so I wanted to ask you, okay, we talked a lot about observational astronomy. Do you use any simulations in your research to compare maybe to your observational data? Because we know that there is a big part of astronomy that's trying to predict what we're gonna find in the universe, and how this is different. How is it different from what you find?
Yeah, I I mean, it's not only like predicting what's going to happen, but when we observe something, we observe it at the stage that we observe it. So we don't necessarily know what happened before or what's going to happen after. The only way to know this observationally is observe as many objects as we can, so we can detect some sort of evolutionary sequence between the objects. But when theoreticians simulate, for example, molecular clouds, they already know what goes in it and they know what comes out of it. So it provides a great terrain for comparison with the type of observations that I do, so they can tell me what might have been the initial conditions that led to the current situation of my filament, for example.
And so, okay, the question now arises, what do you think is the big question to answer in your field? What would you like to answer in your field through your research and all these observations?
I mean, I had to think a lot about this over the past couple of months because I was applying for jobs.
Great, now you have an answer.
I honestly do have an answer. And although there are many layers to this answer, I think one thing that I would really like to know is what set of properties of the filamentary structure that we observe end up forming different types of stars, namely the low mass stars, which look like our sun, or the high mass stars, which are much more violent and they inject a lot of energy back into the interstellar medium and also enhance the chemical composition and so on. And they're very important for dynamical evolution of our galaxies. And I would like to know what happens in molecular clouds, in particularly to filaments, that leads to the formation of high mass stars, and what happens to filaments once the stars are formed. So yeah.
So, okay, so low mass stars and high mass stars are also formed in filaments, right?
Yeah.
But there are different types of filaments, and this is still an open question.
This is still an open question, yeah.
We don't know exactly why it happens, and maybe up to now we didn't have the observations to prove it, right? All this good resolution, and because I guess to observe filaments you need high resolution and sensitivity observations, right?
Yeah, so to resolve these objects we need high resolutions, and also there some things are a bit intuitive. If you don't have enough of a mass reservoir, you can't form a lot of high mass stars, but the details of the physics that lead to the formation of high mass stars is interesting, especially the flow of gas, the motion of gas that happens along the filaments or across the filaments, is something that we still try to understand, and I think it's a very promising field too.
That sounds very exciting, and I hope you get to answer your questions.
I hope so too.
Yes, it sounds fascinating to understand how stars are formed and why they're different. And now we'll change completely the topic and ask you about your outreach in the iAcademic and what it is about, what inspired you to do that.
Okay. Yeah, iAcademic is my podcast, which started in the beginning of the pandemic, I guess, a month or two in to the first quarantine period in Germany. And it is a passion project, and it started by basically my friends telling me they would listen to it if I had a podcast. So and I thought a lot about it, and I think this is, maybe I should explain what iAcademic is about. So this is a podcast discussing, so me discussing with my guests, being human in academia. And we're discussing especially the topics of diversity, being neurodivergent in academia, dealing with imposter syndrome, how disabled academics or how LGBTQ academics can cope with the academic culture, which is not always very accommodating for or to diversity. So that's what we're discussing, and it's been a passion project because I too, as a Middle Eastern woman in Europe doing science, I also feel underrepresented sometimes, and I also deal with or have dealt with throughout my academic life a lot of anxiety, a lot of imposter syndrome, and talking about it helps me. And as far as I can tell from the feedback that I get, it also helps other people to realize that they're not the only ones dealing with the difficulties that come with the excellence culture that we're in.
Yes, this is very important what you just said, because we in academia we study something small and we get close to ourselves, we don't think that everyone else feels the same thing, and that makes us feel even worse. And now with the pandemic, where we're forced to stay home,
Yeah.
and if you're alone at home all day, this escalates even more.
Yeah.
So it's good to get out there and discuss these problems that were they were inherent in academia. And we just need to find solutions for them. So guys, if you haven't heard Sue's podcast, go and listen to it. I put the link on the live chat. I gave your Twitter link, and I guess they will find, right?
Yeah.
So we have one question from the audience, but before that, I have a question for you. If you would, where is it? Where's my question? You encourage students to follow this career path of astrophysics with all the problems that we know it has.
I encourage students to follow their dreams.
Yes.
If they want to be in academia, academia should be for everybody.
Yeah, that's great. That's fantastic punchline. I love it. And we will ask, thank you very much for all these
You're very welcome.
Thoughts and the descriptions. And let me find the questions. We have very good feedback, amazing project. The podcast is amazing. Okay, yes, it is. I've also listened to it. Okay, so we have a question from Tessa Kleti. Do stars form outside of filaments?
Oh, that's a very good question. So I can safely say that most recent studies showed that almost 80% of all protostars in observed molecular clouds are located within the filaments. But these are very dynamic systems, and they might migrate outside of the filaments too. But I think my personal guess is that they all form initially within the filaments, and then they might migrate outside.
Because of movements
Yeah.
Inside the filament. Okay, very interesting. I didn't know that. Good. Let's see if we have any more questions, and then we will move on. What's going on here? Yes. No, but guys, if you have any more questions, write them on the chat and we can answer them later. Again, thank you. And let's move on to the next part of this event.
Mommy, do you grab
Okay. So If you understand Greek, then you understand that my son is very interested in today's event, and he wants to know what people have written on the live chat. So, okay, now we play a game, guys. Okay. Hi, Mom, έγραψες, bravo. My son wrote on the live stream, great. I have a YouTuber at home. So, we play true or false. And it goes like this. I say something, a statement,
Yes.
and if it's true, if you think it's true, you go thumbs up, and if you think it's false, you go thumbs down.
If we're not sure,
If you, okay, and hopefully I got this correct. Okay. The first one. Astronomers are starting to find and measure atmospheres around distant exoplanets. True or false? True. Yes, this is true. And this allows them to understand what gases exist in those gaseous envelopes. Okay, I stole that from somewhere. Very good, 1 point. Good. The second, a molecular cloud is also called dark nebula.
I should know this. There's so many, but there's so many things that molecular clouds can be called.
Yes.
There are different types of.
Yeah, there are also different types of molecular clouds. But
but
this is one of them. And
many the other way, the dark clouds are quite often molecular clouds.
Yeah. Yeah.
Yes, very nice. So 2 points. Among other characteristics, astronomers can measure the surface temperatures, orbits, magnetic fields, and colors of exoplanets.
So repeat again the surface temperature.
So they can measure. Astronomers can measure temperature, orbit, magnetic field, color.
What
In principle, yes, the magnetic field is very difficult. There's a very indirect method, but in principle, everything, yes.
Or this is where we have our expert here. Yes, this is where we have our.
The magnetic field is very, very indirect.
So how do you measure it?
And the basic idea is the brightest radio source in our solar system is Jupiter, and it's bright in radio because it has Io, and Io feeds material into Jupiter. And now this is not a continuous low frequency radiation, but it comes in bursts. So the observation was you see a burst low frequency, and then the question is the interpretation correct? So it is not that you can really measure the Zeeman effect of a planet. And then there are other indirect arguments that it's very likely that there is a planet. But measuring is a strong word.
Very good, very good. So maybe in the future.
In the future, yeah, that's the hope.
Fantastic. We love exoplanet research, and we want to learn more about exoplanets. And
so you should ask also other questions.
Yes. So, okay, now we have one. So three points for you guys. So, fourth one. Molecular clouds are always spherical.
No.
And if you listened before, you should already know that. So it's false. And we learned that there are a lot of filaments, strings everywhere. Fantastic. So 4 points. Okay. We have found at least one exoplanet that has an exomoon.
That is actually false. The reason is there is one claimed detection, but most people don't believe it.
Oh no, why? Poor exomoon.
Yes, because another group reanalyzed the same data and said they don't see it in that data, in the very same data.
On the same data.
And people are very skeptical then. I mean, there's the claim to, there is a claim, but
I will share the link in the chat so people can judge for themselves, because
exactly, you can judge,
Yeah.
whether that is a clear detection or not.
Yeah, it's all about peer review in astronomy. So
Yeah. No, I mean, it's fine to publish this result, but it's also fine that other groups check the same data and said, we can confirm it or disprove it.
fantastic. So I will give you the point, 5 points. Okay, I will do like this because if you do like this in Greek, it's not good. So 5 points. Sue might know that. Okay, right. The smallest cloud. Oh, what is that?
The smallest?
Wait. I don't know what I've written here. Okay. So we have clumps inside molecular clouds, and the smallest clump can be 100 light years across.
The smallest 100 light?
The smallest.
No, there are smaller ones. 100 light years, the smallest. Oh, no.
Yeah.
No. Well done, guys. Congratulations. 6 points. So my sources say 1 light year across.
Yeah, I had to convert light year in my head to astronomical units.
To do light years. Believe us, we never use light years. It's only for outreach. Yeah, so these clamps that Sue was referring to also before, right? So they're like 1 light year across or something, the smallest ones. Good, 6 points. We have 2 more. Oh, okay. Let's see if this is true also, Ike. Astronomers found an exoplanet which is leaving behind a trail of material because of the star. So the material is vaporized while it's orbiting its star.
Yes, this is...
I don't know anything about this.
Well, that's the observation from the one guy in Graz, and he measured the calcium lines, and the calcium lines is a line in the spectrum of a star, and it scales with the activity of the star. Now you can measure the activity, and without observing this line, you know how strong it is. And so for every star, you can either measure the line and know the activity level, or you measure the activity, then you know how long. And he found one exoplanet, which is the only star known where the line is completely absent, but the star is obviously active. And he argued, well, the reason is the evaporation of the material of the exoplanet, which forms a ring around the star. And then in this line, we cannot look through to the surface of the star. So there's a cloud around it, which looks like a torus. And in this case, I'm pretty much convinced that he's right, because he now has a second one. And it's again other arguments, and I think that's correct.
Ah, very nice.
Interpretation.
So,
and his name is...
the name is D.S. Tukab.
No, the name of the person that had published it. I know him. It comes to my mind in a second.
I have the research right here. It's from TESS survey, Elizabeth Newton.
Yes, she also did this. Yes. I was thinking of a different name. Yeah. She also.
Yeah, sorry. This is the paper that was linked to the survey. I put it also on the live chat, so people can check for themselves.
Yes.
Okay, 7 points. You guys are doing great. And last one.
Extragalactic. No, it has to be extragalactic.
Oh, extragalactic. Huh. Then I have to think something from my brain, because
yes, select something from your brain. Extragalactic. Let's see.
Improvise.
Galactic. Okay. Wow. Extragalactic. I cannot think anything right now. Damn it. I should look at my previous true or false.
Not something special. I mean, we are not experts in extragalactic. That's something.
Okay. I will ask you something about active galactic nuclei.
Yes.
Okay. So these are the active galaxies in the center. Is the active nucleus in the center of the galaxy. So an active galactic nucleus can emits so much light that overshines its own host galaxy.
Yes.
There you go. That was easy. I am very good today. I'm in a
called a quasar.
It's called the quasar, yes, and it emits so huge amounts of energy to the environment. It releases so much energy that when we first discovered them, we thought they were stars. That's why they were named quasi-stellar objects. They were
Yes.
optical. And but then we realized that they're not stars. It's just the nucleus is so bright, it overshines the rest of the host galaxy. Imagine Andromeda, for example, but then imagine Andromeda had a very, very bright nucleus that is brighter than everything else. So you would only see the point.
Yes.
Very good. Well, congratulations. This was the true or false. You passed.
Yes.
Give yourself an applause and have a drink. And now we will go to.
I drink tea.
Yes, for your
Me
tea.
too.
It's is it Long Island iced tea?
Oh, I always like really green tea. And well, I had actually 3 visits to China, and there you drink green tea. And once you get used to green tea, you really enjoy it. When you drink the first green tea, it's awful. The second one is better, and the third one. And now I really like green tea.
Yeah. I will agree to that. The first time I ever tried green tea.
And just one thing, there is in one of these cities, not so far from Jena, there is a Japanese garden, and they have a Japanese tea house where you can make an almost original Japanese tea ceremony.
Okay, when everything is open, we go there.
Exactly.
Okay, before I start with asking you about your life and career, we have a question related to the true or false in the chat. Okay, I have 2 questions, and I will answer you. I will ask you now, so we don't lose track of the questions. So, Ike, what would cause a planet to evaporate like this? That was the question.
Ah, that's actually the subject of my research. It is a gaseous planet, like if you have a planet and around it an atmosphere which consists out of hydrogen, and if the star emits a lot of X-ray and UV radiation, then the upper part of the atmosphere is heated up and evaporates. Don't worry, it happens also on Earth, but not in a quantity that our atmosphere is gone tomorrow. And also that is the reason that when you go higher and higher in the atmosphere of the Earth, it gets colder and colder until a specific point, and then it gets hotter again. And that is the UV radiation and the X-ray radiation from the sun heating up the outer layers from the Earth atmosphere, which actually evaporates, but only a little bit. And don't worry, the Earth's atmosphere doesn't evaporate. And if you have a gas planet, then the whole atmosphere can evaporate, and then only the core of the planet survives.
Is the core? It's not that.
Well, well, in the case of the Earth, the core is the whole Earth, and the atmosphere is just a thin layer. But in the case of a gas giant like Jupiter or so, the core is really tiny compared to the rest. Now, a planet like Jupiter has too much mass; it cannot evaporate. But in many planets, we think that they are evaporating, and even we see some where that lose tremendously the atmosphere.
Great, thanks for this explanation. We will ask
Thank
more.
you.
Okay, one more for Sue, because I will
Yes.
later. Okay, Sue, it's a personal question. The audience wants to learn the name of your cat.
Oh, this is Fiona.
Oh, very nice name. Amazing. And she's all nice, laying up there on the couch. Fantastic. Okay, now let's go to Ike and tell us how you got into astronomy and your career path, and what brought you to this beautiful place we call Thüringer Landessternwarte Institute in Tautenburg.
Yes, so I more or less tell a little bit the funny parts or the short version. So first of all, when you ask most astronomers how they got into astronomy, they say, oh, already as a child, I loved the stars and looked at the sky and so on. That's the usual thing. In my case, also, I liked it. But I have to say that then also with friends, they always said, yes, but astronomy is always the same. These things were discovered ages ago. There's nothing new. And I had also this opinion. I thought, oh, this is, I don't want to do it as a job. It looks nice, but I don't want. And then when I was a school child, and that's the reason why I like to take also school children, because it changed my life. My parents said, oh, I should learn English. And I said, and then they said, perhaps English connected with astronomy. So I was sent to UCL, University College London. Now I hope you are ready for this, because I tell the number. This was 1978. Okay, and then this, so a long time ago, and at that time, my impression of Mars was it's a little dot in the sky, and if you look through the telescope, you see red, and maybe you see something. And at that time, there was just the Viking landers, and they had an orbiter producing all of the wonderful images, but they had not appeared in the newspaper. So I went into this and did some work there, and actually just ordering the library. And then they said, by the way, do you want to see how Mars looks like? And I said, yes, yes. And they had the stereo cameras. And I looked down and I thought, this is unbelievable. Mars was for me just a dot. And now I see mountains, landscape, rivers. And that completely changed my mind, because in this way, I thought really a new instrument can change the direction. And also today it is, I find it fascinating. Normally you think science is a puzzle, you add up puzzles. And then comes something and the whole direction changes by 180 degrees. And what I like very much in exoplanets, we are just in this phase. Now I don't say any names, but it's exactly like in the textbooks. Mm-hmm. Because we have a dramatic, I would call it, it's like a Keplerian change of direction. And as it's always reported, it is like there is one group of people that is, say, slightly older, I have to say, that are absolutely unwilling to accept the new view and say this is unproven and we don't know. And they are really fighting against this new view. And a group of, let's say, younger people have this new view. And they have, because we work in a team, tremendous problems in publishing a paper where everybody honest, where everybody agrees to it. Now I have one fantastic colleague, and I don't tell her name because then everybody knows. And she's extremely smart in this. And she wrote one paper 25 pages long. And of course, when you get a paper from a team, it's 25 pages long, you read it, yeah. And in this is such a section, which is the most interesting one, because it says our current picture is absolutely wrong for this reason. And I like it very much. It went through all the big heads, and the big heads never recognized that their name is on a paper that says what we did for the last 20 years was complete nonsense. Awesome. And now she published the second one, and I was like, oh, fantastic. It's another paper from her. It's again, the same thing. And again, these people that are in principle against the new idea did not even recognize what is in there. Amazing. Because she is so amazing in hiding this idea. But when you read it careful, you see the new ideas in there. And that's what I really like, in science, that it's not a continuation, but it changes occasionally completely the direction.
But it also depends on new observations and data we get.
Exactly.
I mean, this is what science is. We cannot have, our eyes to one place. We have to evaluate the data. And if it's different, if it tells us that our theories are different, wrong, we have to change it. But this also tells you, Ike, that co-authors do not read papers.
Yeah, exactly. And that's why the trick works. And one remark, because you mentioned the AGNs, and today when you ask anybody, then they say, oh, AGN, there's a black hole. When I made this first practicum in this observatory, people were absolutely convinced that the idea with the black holes is complete nonsense and a speculation that some idiots made, because the accepted picture that everybody was telling, an AGN, is a triggering of supernovae. In the nucleus are many supernovae, and when one bursts, it makes the next star a kick, and that explodes a supernova, and that's why they are variable. There are no black holes, there are just the supernovae. And then came this one observation of Cygnus X1, which is of course not an AGN, but a nearby black hole, where they measured the mass and said, by the way, this is a black hole. And then, of course, this idea of the AGN with the supernova was dead the next day.
I didn't know about the supernova. I know there are many different interpretations of what this black hole can be, and still we really
yes, but at least this picture of the black hole is there, and that was also something that was a strange idea of a few very weird persons. Until this was found, and that's actually what I like. And yes, this change in the direction,
because science moves and you also moved. So where did you go from, you said?
Okay. Now one thing which is also a little bit related, that's actually why I do the public outreach, that is, I unfortunately lost my parents very early in life when I was a teenager. And now I had the opportunity, because at that time I have to say, the German state would, in this situation, pay the whole study.
Okay.
And since then, I also think this is a unique moment that I had this chance. If I were born 20 years earlier or 20 years later or in a different country, probably I would never have this possibility. So I also always think, how many talents are we missing because we don't give the opportunities to everybody. Presumably, I would say to a small fraction of the people that would be capable in studying. And yes, and so yes, and then what I did was, I was born in the north. I went to the south and actually studied the sun. And the sun was very interesting because at that time the neutrino problem was unsolved, and we didn't know why the corona is so hot. And I thought, this is amazing. We don't know more or less why the sun is shining. Everybody sees the sun in the sky, and we do a lot of science, but we don't know why there's light coming from it because of the neutrino problem, and which was solved only later by particle physics. And I thought, this is amazing that the most prominent object in the sky, we don't know what it is. Well, we know what it is, but we don't know how it works. And then I worked on the sun, and then when I finished, I should make one remark. At the time when I studied, there were absolutely no regulations. You had to do, basically you could study whatever you liked. And then after 2 years, you had one exam. And then after 7 years, another exam, and nothing in between. And after 7 years, you were expected to know everything.
Okay.
and not this, you should take this in this lecture. And I for that reason, I also took many very bizarre lectures because I was interested in this stuff. Yes, and so I was studying the sun. And then actually my PhD father said, well, you know, astronomy is a small field and the sun is even smaller. And so if you think you want to drop this subject and do something else. And so actually then I went to the Max Planck Institute in Heidelberg and studied actually star formation. And then when I was finishing the PhD, I saw a job advertisement, and at that time there was the absolute mass unemployment, and people said, nobody gets any job, and so on. And I said, I just write to it, and they said, you have to practice this and have to do it 50 times, then you get a job. And then I just submitted. I was for some reason invited to the interview, and in the end I got it. And I thought, oh, I never thought about this. And in the interview, I was so relaxed because I was so sure that I would never get it.
Maybe that's the trick.
Is this your advice for interviews?
Yes. And I mean, my application was written in the style, I have no chance. And in the interview, I thought, oh, this is nice, because it was in London. It's a nice day. I can go to London and visit something like the tower and so on. And then I have 1 hour this interview. And anyway, they don't take me. And then next day I got a call and said, oh, by the way, I can take you. And the Tautenburg thing was the same. I was in London, I had a postdoc, and I had already, and then they always said, well, if you stay for a long time in Britain, you lose the contact with Germany and it would be very difficult. So you should take one postdoc in Germany. Then I applied for a job in Tautenburg, heard absolutely nothing. And for months, then I signed a new contract. And then the director from here called me and said, oh, you wrote in your application how this and this instrument works. Can you explain me how the instrument works? And he was asking these questions for an hour, and I thought, this is the strangest phone call I ever had. He's asking, he doesn't consider my application and asks how this instrument is working. And then in the end, he says, oh, yes, you should come to an interview.
Amazing.
And so I ended up by accident in Tautenburg. And also, I think that somehow all this application was so strange that few people applied. That was my reason. And with London, I think that was, so I think with the jobs, there is more luck into it than anything else.
Yes.
It's, I would say 80–90% is luck.
Thanks for saying that. I think that's very important to just.
Yes.
Yeah, but, you know, you have to keep strong. And also, I like your approach where you said, okay, I will not get it, I'll go sightseeing. It's not
exactly.
the end of the world. You know, it's not the end of the world. And we should approach life like that, because something else will come.
Yes, yes, yes.
And that's very good thing. So, you know, it doesn't get you down.
Mm-hmm. And then afterwards, maybe one remark. Of course, Tautenburg is very nice, but after a while you get bored. So I took the opportunity to spend half a year in other institutes.
Great.
Yes. In Spain and Austria and so on. And
oh, amazing. To the nice places. Tautenburg is very beautiful also.
It's very beautiful, but if you stay there very long, then you get bored after a while and you say, I would like to see something else.
In the times where we could travel and, you know, be visitor astronomers, we could do that. Now we're happy because it has snow. But so why exoplanets? How so from the sun, you went to star formation.
Yes, and then exoplanets.
You're studying exoplanets and how they lose their gas.
Yes, because actually that was my wish before studying astronomy, was actually studying biology. Now exoplanets is a subject where the two more or less come together, because the key question we want to answer is there a possibility for life on another planet? Or is presumably yes somewhere, but it could be very different from the Earth. And trying to get closer to the answer to this question. And my hope is still that at some point that there will be evidence for life, and it will be like always, a claimed indirect detection and lots of discussion what it is. But I find it fascinating that to combine the two, the astronomical aspect with working also with biologists and learn from them.
Yeah, it's a new field, right? Astrobiology. So
exactly.
It's very important in what you said to try to understand if there any of these exoplanets that we're discovering now. We're what 4,000?
Yes.
Yeah, 4,000 exoplanets with Kepler and TESS. So we have a very large number, and I don't know how many candidate exoplanets and how many of them. So what we're looking is exoplanets like our Earth, right? a habitable zone, right? So explain to us a bit about this habitable zone and what we're looking for.
Oh, now it gets difficult because I don't like the habitable zone.
Oh, why?
The reason is that, first I explain it. The habitable zone was invented actually 20, 30 years ago because somebody was saying, I think even before the first exoplanet was known, there was the habitable zone. And somebody calculated, okay, you take the Earth with the Earth's atmosphere. If it's too close to the sun, it's too hot. And the water, if there's any water, the water will boil and become steam. And if it's too far out, everything will be icy. And in the middle is a zone where you can have an Earth-like planet with liquid water. And that's defined the habitable zone. Now, the problem with this concept is that when you think how life on Earth formed, there are different ways to it, and there are basically two possibilities. One is deep in the ocean in these so-called black smokers, and the other is, which is the modern view, that is in a kind of cold water geysers, where the water pressure in the water is 100 bar, and where there's carbon dioxide inside this geyser. And actually the second picture is very, very convincing. So let's assume this. Where do you find these in a planet system? Well, you don't need the habitable zone for that. That thing can be in the outer solar system. And so that is the idea that Europa and maybe Enceladus could have an ocean, and in this ocean could be life. Mm-hmm. And now when you think about it, all the specialties, what you need for life on Earth, these are very special conditions. But when you think of Enceladus and Europa, then you think, well, this is presumably every planet system has such a thing. An icy body, that's typical in the outer solar system. Ocean, because of tidal interaction, that's also typical. So I'm actually in this group of the people that says life is presumably very common in the universe. Unfortunately, it's very different from the life on Earth, because it could be that it's more or less these other habitats which are Europa-like. And in terms of biochemistry, it would be similar to our life, because carbon and nitrogen and so on form large molecules which we need for life and so on. But the rest of the environment is completely different. It's an ocean, there's above it's an ice layer and so on. And I think presumably this is the most common ecosystem in the universe is like this. And maybe something like the Earth is the exception.
Mm-hmm. So can we detect these ecosystems like Europa and Enceladus and other?
I hope that, I mean, the launch of JUICE is in a few years, next year, I think. And JUICE will actually study the icy moons of Jupiter. Mm-hmm. And I don't think that they make a real proof that there's life, but I hope that out of JUICE comes data which makes it very plausible that there is life underneath one of these ice shields. And then comes the big thing, because you have to land there, you drill a hole and go into this ocean with a submarine or something. Good luck. But yes, but of course we are a little bit more lucky because there are cracks in the ice shield of Europa and also Enceladus. Mm-hmm. So some of the material from the inside of these moons is coming into space, and the satellite can probe these. So
you can detect them without drilling, right?
Without going inside, and one can then argue, okay, we found already not we, but astronomers, it's the amino acids and so on, and you can all analyze the building blocks for life, and then you can say, okay, it's very plausible.
Okay.
On the same side, on the Earth, we have also a lake underneath the Antarctic shield, completely shielded from the sun, no sunlight, nothing. Underneath, high pressure, and people went drilled inside because it's on the Earth, and astonishingly, there is life.
Oh,
So
wow.
even on Earth, we have this ecosystem.
So this ecosystem was never in contact with.
Not for the last few million years.
Okay.
And still there is living organisms. So life can exist in very strange places, and maybe we are the strange place, and things like this is the normal.
Yeah.
Maybe we are just the exception.
Maybe we're the exception, or maybe we don't have the right telescopes yet.
Exactly.
This exception.
Or the communication devices.
Sorry?
Or the communication devices.
City.
Yeah, that was my question. How do you think in the future, this is very sci-fi question, how do you think in the future we will be able to detect life form outside our solar system, or in our solar system, we don't know, outside the Earth, let's say, that is like us? Do you think first we will be able, and how?
We made a questionnaire in one of the meetings. And 80% of the people have of the researchers on exoplanets think that simple life forms, single cellular life forms, will be so common that we will be able to detect them at least indirectly, and they will be very common. Now, if these simple life forms exist, then there's a good probability that complex life forms also exist. But it could be that it's so rare that we won't detect them. And if we do, I mean, that will be so different from what how the life on Earth is. Also,
do you believe that SETI, that is trying to detect radio signals from space, from extraterrestrial intelligence, for example, do they have hope or not?
I think you should do it because they are using existing radio telescopes, which are there anyway. And also one of the city experiments was done with the Parkes radio telescope, and they had a hitchhiker detector. So the radio telescope was doing normal science, and the hitchhiker would look in a slightly different direction. And so it would randomly scan the sky, basically at no cost. And the same has been done with FAST, this 500-meter radio dish in China. Now, for fun, because I do the public talks, you can calculate if there's a civilization like ours, we also emit radio waves because of television and radio and all kinds. And if there's a similar civilization, how far could we go? Now, with the classical SETI, that would be 1 parsec. Oh.
How much is that in light years?
3.2 light years. There's only 1 star inside. So 1.
Yeah.
Okay. And then with the VLA, I also calculated it's like 100 or so. And only with FAST, with this big thing, they can
China, right? The radio telescope, which is
which looks almost like the Arecibo. It's only larger. It's in Yunnan. Actually, in terms of landscape, a very beautiful area, absolutely amazing.
Yeah.
And there they can study 2,000. Now you can, back of your mind, calculate what's the probability that they find a civilization, blah, blah, blah. That amongst 2,000, there's 1. And my conclusion is you should look for it. But the chances are very low. And when I was actually in Austria in an institute, we were kind of sarcastic and said, because how human beings are now behaving on the Earth, and we said, it's actually much better if you look not for existing, but for the things which are after this. And then we said, oh, let's calculate it if there is not intelligent but stupid life.
like what we're living now.
Stupid life that destroys the culture.
And then we look for uranium and plutonium isotopes in the atmospheres of planets. And then we calculated that actually these would be easy to detect because it's a unique feature. And we wanted to publish it in one of these, but not main journal, but another one. Then we checked on the internet, and actually Frank Celsus, an outstanding astronomer, had already published this idea, the post-stupid civilization detection and the probability to detect it. And he said, well, you know, the probability that human beings die out is 1. And if you calculate that number and the half-lifetime of these radioactive elements, you find it.
Amazing. It's easy to find stupid life.
So that's a little bit sarcastic, but I like this kind of strange humor.
I like it more than finding intelligent life. It's a buzz. Okay, you told us about your outreach and the TV series that you do.
With the outreach, one more thing to it. Normally, because we study the universe and so on, you think that when a public group comes, they would ask similar questions. Now, I lived in Northern Germany, Southern Germany, East and West. And what I find amazing, that when you are in one part, they all ask very similar questions, but in the 3 directions of Germany, they are already completely different. And I also participate in other countries in there, like Australia and so on. And I find it amazing because astronomy is in principle something about the universe. But when you speak to the public, in every country, they have a completely different kinds of questions that they ask.
What do they ask?
The most urgent question.
So what is the most asked question in this region?
In this, well, that's a little bit funny because of the Zeiss company, they always ask, or they like to ask very local things like, oh, how this was done, who was involved in building our telescope and so on. So that is a lot of the questions here. Normally we say the typical question is the triangle, which is, what about black holes? What about the Big Bang and is life in the universe? That's the normal questions. And I find it amazing when you come to many, many groups that don't ask none of these.
Oh, interesting. They always ask me about very exotic things that sometimes I don't even know. Believe me, I got some questions sometimes
Yes.
about, I don't know, parallel universes that I had to Google. But anyway, so last question, and then we will go to the question. Would you encourage people to do what you do, although you had this unconventional path?
Yes. I would always encourage, and also I fully agree. You should do what you like. And because when I started studying, I also went to such an office for information, and I said, I want to do this exotic thing. And then inside was a person that was doing an ordinary, and he said, well, if you do the ordinary thing, there are always many other people, and always the people that like that stuff will be the one which will come into this position. And so whatever your dream is, you should go for your dream and do what you like. I have one example in our family, my cousin. I mean, the family always said, when they were still there, the young generation is crazy. So he was interested in music, and then everybody said, oh yeah, normal music. And then he learned Norwegian, and then his supervisor said, oh, we found in the last valley in Norway a very old man, and how he played the violin is like we see on pictures from medieval times, and nobody knows how it sounds like, but apparently in this last village behind the mountains, there's still an old man that plays the violin like they did 500 years ago. And his PhD was to spend 2 winters with 2 meters of snow on this farm and learn how this old man played, because that was a historic thing. And then everybody says, this is the direct way to unemployment. This is, you will never get with this job. And then I offered one job in Oslo, the conserving the Norwegian traditional music, and there was only one applicant, and he got it.
We call this in Greece photographic. Fantastic. We have a question. Thank you, Ike, so much.
Yes.
We learned so many things. And I wish we had a lot of time to talk more about all this, and with you guys both. We have one question. I don't know exactly what it means. What about looking for some kind of optical communication? I think it refers to...
yes, that's the optical... the optical city, and you know the story was that's for sure the question after Tabby Star, right? No, while optical communication is there, that's the idea that other civilization would know where we are and beam a laser in our direction, and we would detect it as a signal with a telescope. Theoretically, yes, one can look for it. And Tabby Star, of course, went through all the press. They said if there's an alien civilization building space station around the star, you would see a very distinct form of the light curve. And of course, they found a star like this. And in our colloquium, Hans Steeg gave a very nice presentation because he studied Tabby Star. It's dust clouds and not civilization, but it went through all the newspapers that Tabby Star, there's a civilization. Yes, optical is of course also something. By the way, I like to read old books. In 1910, they thought that they had discovered an optical signal from the civilization on Mars with exactly that method.
But no.
Well, for several years, they were absolutely certain that the Martians had sent a specific signal to the Earth.
Great. Well, thank you very much, Ike. There's a lot of questions about life in the universe.
Yes, yes.
It's a topic that, you know, it can never end. And so there is one question related to AGN. So that's me.
Oh,
I will answer to that.
for you.
That's me, yes, because I'm the expert here. So the question was, what about inactive? Okay, so when I did my undergrad, we used to call this normal. So we said the active galactic nuclei, the ones that have this active nucleus and emitting a lot of energy to the environment. And these also have different types, and at different wavelengths we observe them with different properties. So it's a very complicated topic. And whatever was not active was a normal galaxy. Now we separate them in star-forming galaxies, inactive galaxies, and starbursts, so a lot of star formation. So I will give you some numbers, for example. Star-forming galaxies, which do not have an active nucleus, form stars, 10, 20, 100 stars per year. Our Milky Way forms 1 star per year. Starbursts form a lot of stars per year, okay, like above 100, above 50, up to 1,000, depending on how active they are in star formation. And then active galaxies usually do not form stars. So active galaxies, the ones that have an active nucleus, and they occupy usually an elliptical host. So they do not form stars, but more observations reveal that we find objects that have active nucleus and also form stars. So it's a very complicated issue with a lot of names depending on the wavelength you observe and the data you have. If you have more questions and you win the quiz, I can answer all that. and now we will go to the quiz. So,
and we have to open this link which you sent, right?
Yeah, so I put the link on the chat, and hopefully it will work.
And at least I see something.
Yes, so let me close a few things. I have too many things open. I will share my screen because I have slides.
Okay, so I can close this and
you can play. So you
and
play
can we
in the
click?
link. You can play in the link I sent.
Okay. Just a second, then I have to open this.
So it's a different format from last time. Now you get this Google form, and at the end I will get a number. I will get your questions. You have to sign up with your email address. You don't have to give your name if you don't want to, but you have to give your email address. And at the end, the winner will get notified. I will call their name or their email address, or I will send an email depending on what you provide me with. So I will wait a few minutes so you all sign up. Don't Google. I will put a timer. 30 seconds per question, okay? I'm very strict. I will be very, very strict. There you go.
So you read the question first, and then we
Yes,
click
I
on
will
it.
read the questions.
Mhm.
Okay, I will read the questions. It's annoying that we have a small time lag from here to there, from our live to our live audience. So okay, right. And here we go. Okay, did you get it? It's 9 questions. You have to answer them, and whoever wins gets a private, let's say, astronomy discussion with me. Okay, you can also play Ike and Sue, and if you win, we will
Yes.
have to discuss together.
We can discuss our papers.
Okay, let's see. So the first question is, in 30 seconds, the red glow and the larger shape of the Hart Nebula are all created by a small group of stars near the nebula's center, a giant star emitting huge amounts of energy, the black hole in the center of the Milky Way, or a neutron star spinning 100 times per second. Okay, let's go to the next one. I put 30 minutes instead of 30 seconds.
Oh.
And I was like, what's going on? Okay, I hope you got that. Let's see the next one. 30 seconds.
Oh.
Hart Nebula is located about 7,500 light years away towards the constellation of Andromeda, Cassiopeia, Aquarius, or Camelopardalis. So our quiz today is all about hearts because, you know, it's astronomy lovers. Oh, yes. Thank you very much. Yeah, okay, shut up. Next question. Okay. At the center of, Hart Nebula, sorry about the typo, used to live a neutron star, a black hole, a macroquasar, or a brown dwarf. At the center of Hart Nebula, what used to be there? But it's not anymore. 5, 4, 3, 2, 1. Thank you very much. Next question. So, there you go. What is a macroquasar? It's a smaller version of a quasar, a very massive quasar, a quasar at the beginning of the universe, and a quasar in another galaxy. That's a very difficult one, right? Mm-hmm. No one will get it.
I mean, according to the astronomer logic, it should be the exact opposite of what it says it should be. So,
right.
A quasar in another galaxy, in a galaxy far, far away. Good. Okay. So, ding, 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 ding. Next question. 30 seconds. What is a nebula? A cloud of gas inside a galaxy. What we used to call galaxies. the last stage of a massive star, and what is left after black hole collision. Very nice. I hope you got that. It's a tricky one. Next one. The term nebula was used to describe any diffused astronomical object, including galaxies beyond the Milky Way. True or false? Let's see how many astronomer lovers we have today. All right, 2, 1. Very nice. Oh, I love Pluto. Pluto is a dwarf planet in our solar system with an area forming a heart. True or false? So if you have seen pictures of Pluto, you would know this. The most recent pictures of Pluto. Pluto is no longer a planet. When I was a kid, it was a planet, and then all of a sudden it was not a planet anymore, and that was very confusing. So it's what we call a dwarf planet. Okay, and I will tell you more about it at the end, during the answers. Next one. The heart of Pluto is 1,000 kilometers wide and composed of hydrogen and helium, carbon dioxide and nitrogen cyanide, nitrogen and carbon monoxide ices, methane and ammonia. Right, so what do we find in very icy environments, very far away from the sun, far, far away from the center of our solar system? Yes, thank you very much. Okay, that's the last one. The most dramatic end to a galactic love affair is when two black holes collide, a black hole and a neutron star collide, two neutron stars collide, or a black hole devours its companion star. Okay, you will not find an answer if you Google this, so it's biased. And let's see if you have the same preference as me. Right, and time is up. And before I go to the answers, guys, I will stop the quiz. So we don't accept any more answers, but one response. Why do I only have one response? Let's see. 2 responses. Okay, guys, I hope you submit soon. Okay, I will leave it for another minute or so you can submit your responses because of the time lag. And then we will go to the answers. I hope you know the answers. So how did you like the quiz?
It
was everything but easy.
No, come on. It's a hard nebula. Tick, 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 tick.
Yeah. This I know.
Yeah, only that. Okay, good. Thanks for responding. Right. So I will wait a bit more because of this of the time lag, which I hope Zoom will solve at some point. And then I can close the. Okay, let's go to the answers, and then I will close it. I will be good today. Right. Let's go to the answers. There we go. Good. The answers. So, the red glow and the larger shape of Heart Nebula are created by a small group of stars near the nebula center, which expelled gas and made this very nice shape of the nebula. Okay, so it's the first one. The Heart Nebula is located about 7,500 light years away towards the constellation of Cassiopeia. Okay, it's a W in the sky, so it's very easy to spot. The third one, at the center of the Heart Nebula used to live a macroquasar that was apparently expelled. So it was kicked out of the system. And that's why I ask you, what is a macroquasar? And this is a smaller version of a quasar, where you have something emitting, again, large amounts of energy, but not like in a galaxy, but something inside our galaxy. So it would be like a black hole with a companion star that accretes matter. So matter is circulated around this black hole, and then energy is emitted also at radio wavelengths in the form of jets. And then the microquasar will get the material from the companion star, and the companion star will lose its material, right? Right, what is a nebula? So it's a cloud of gas inside a galaxy, yes, but this is also what we used to call galaxies, so it was a trick one. It's not what we say a molecular cloud in the sense what Sue described to us today, but a nebula is composed of gas, right? The term nebula was used to describe any diffuse astronomical object, including galaxies beyond the Milky Way. This is true. And up to the early, was it 20th century, 19th century, 20th, with Hubble. Help me, astronomers. Was it 19th or
1920, so 20th century.
20th century, thank you. With Hubble discovering that these objects that had this fuzzy appearance were actually outside our galaxy, like Andromeda, for example. So Andromeda was called the Andromeda Nebula in the beginning. Pluto, you see the picture here, has a heart. It's a lovely planet, dwarf planet, okay? It's a lovely dwarf planet in our solar system that has an area that looks like a heart. And this area is composed of nitrogen and carbon monoxide ices. So everything is very frozen there because it's at the outskirts of our solar system, very, very far away from our sun. So not a lot of heat reaches out there. Okay. And that's the last one, the most dramatic intergalactic love affair. Of course, everything is dramatic because when you have two black holes colliding, you know, it's a huge event. And then you have the creation of, while the black holes are circulating, they emit gravitational waves, and we detect them here on Earth. That was the discovery a few years ago. It's the same when a black hole and a neutron star collide. So it's all very dramatic. But the most dramatic of all is when you have, let's say, a love affair between a black hole and the companion star. And the black hole just cannot have enough, you know? It has to suck everything up. So it takes all the energy, all the matter, everything from the companion star forever and ever. And the companion star can disappear. And that's the most dramatic love affair in the universe. Okay.
I thought that the energy which is in these gravitational waves is extreme. And I always thought that I had heard this number, that the energy in this moment where the gravitational wave happens is equivalent to all the energy in electromagnetic waves in the universe at that moment.
Okay, I don't know this fact, but maybe that's one for the next quiz. Mm-hmm. Yes, that is true. That's a lot of.
I just remember that they said they can detect it over such a huge distance because a lot of energy is in this gravitational wave.
Yes, I'm not sure about this fact, but we can check. Mm-hmm. For sure. So guys, so we'll stop now the quiz. Thanks very much for playing. I think that's it. I will stop the responses, and hopefully I will get Oh, very nice. Okay, right. So we have our scoreboard. I will share my screen. Thanks for playing. Only 7 people played. Why?
Oh, only 7.
Why?
And Evangelos won because he always wins.
Let's see. I don't know if Evangelos played, but we have 7 people playing today. At least 7 people before I closed the 7 that submitted. So Paul from Bonn, you won. Congratulations.
Alex also has 7.
Alex has 7, but Alex is an astronomer.
Ah, okay.
Okay, right. Alex has 7. Let's see the responses. Guys, thank you very much. They were not so easy. Okay, that was not so easy to get. You did not get that. That was the most easy. And this one, Pluto, of course. Yeah, sorry about that one.
And the last one, nobody got? Or what does great mean?
No, the 3 answers were not for, for this one. But okay, so Paul, congratulations. I guess we're on an astronomy date. So we have to arrange a time. Guys, thanks for playing. And I will stop sharing now. And we go to the last part of our of today's event. Thanks for sticking until the end. Let's see if we have any questions from the audience before I go to the last part.
Yes, I know.
Someone says, I understand now the logic behind the last question. Yes. Very nice. Thanks, guys, for playing. And if you ever have questions, don't hesitate to write me an email or contact me on social media. I will give all the information at the end. So, my lovely astronomers, my lovely guests, today we will play the last game, which is Never Have I Ever. And I used to be horrible in this game, to think of things, you know, when we play with friends, when we used to have lives. And now I try to make an academic version of it to, you know, it's like your podcast, Sue.
Yeah.
Expose academia.
Oh no.
Yeah, okay, it's okay, it's light, it's not too bad. So in this one, I say, never have I ever, and something. So if you have done it, you drink. And for most of them, I drink. So, never have I ever written an erratum. Seriously.
Erratum? Yes, I have.
Okay, so an erratum, for the guys that don't know from the audience, so when we do publications, when we publish our studies on astronomical journals, sometimes we make mistakes, but the paper is already published. So in order to correct it and not leave it with a mistake, we write an erratum that is linked to our paper and says, oh, for example, this equation was printed wrong, or this plot is wrong, this is the correct one. So something small. This means that we don't retract the paper, but we can keep it there with the correction. And this happens, it happens even to the best papers with a typo. It can happen. It's not too embarrassing. No? Okay. Never have I ever called in sick to work just to have a break. Cheers.
Cheers.
Because we're all human.
Yep.
And we need a personal life. Day. Sorry. Yes, that. And also we have to appreciate work and life balance and not to burn out, because this is a very big problem in academia, that we never stop and we do not appreciate our health. So we need to stop and we need to take a breather. Right. So never have I ever watched Netflix at work. Netflix at work. I don't think I ever watched Netflix at work. But I have watched South Park when I was a student, a PhD student. At lunchtime, I didn't want to go out for lunch, and I was like, okay, I'll sit on my desktop, and I watch South Park and eat.
But reading the newspaper or something, that is also very common, and I have to say I do this.
Yes.
I mean, also to have a break and so on. At some point, you switch off the stuff and you read the newspaper.
Yes, and also sometimes watch astronomy videos on YouTube. Or, guys, if you want a break, you should listen to Sue's podcast.
Yeah.
Mm-hmm. Oh, by the way, can you send the link at the end? Or?
Yes. Is it for Spotify?
I can send it, I think.
And I will also post it on our live chat. So the next one. Oh. Okay. Never have I ever thought of taking a year off and traveling around the world and leaving everything behind.
Never ever? No, I have done this.
You have already
no,
done
no, but I considered. No. Yes, sure.
Yep. I have actually done it when after my bachelor's, I took a year before my PhD. That was the most fun year ever. Because before we had lives, we could go out.
Mm-hmm. Exactly.
Yeah. So now taking a year off and staying home.
Mommy?
Yeah.
Get subscribe, get a notification bell.
Okay, I have one more. Never have I ever. And then there is a question from the live audience here in this house for you, the live audience on YouTube. Wait for it. So never have I ever thought of leaving academia. So cheers. Because academia is a tough place. And balancing motherhood and research and traveling everywhere and wait for it. And not being able to finish your sentence sometimes.
One question which is interesting because astronomers travel a lot. Did any of you ever counted how many countries you have been?
Yes.
I have not.
Well, not that many. I've been to the US, Spain, France, Italy, Greece, Cyprus, Japan, somewhere in Scandinavia. UK, I don't know, let's say 10. But the most challenging thing about having, for example, a kid and want to go to a conference abroad is that you have to take the kid. If the kid is at school, they cannot leave school. So how do you go? Mm-hmm. So the logistics behind attending a conference before the Zoom era was insane. So for one time, there was 1 year, I wanted to go to 2 conferences in June. And within a month, I made 10 flights because I took my kid to Greece to my parents. And then I had to go back and forth from Greece to Germany and to the other places in order to attend the conference. And these are private money also. So there's it's a very big, complicated issue. Yeah. Yes. Okay. So we have a question from the live audience here.
Yes.
Okay. To the guys at home watching us, have you
liked the video and subscribed and hit the notification bell? Because do it.
Me not. No.
Okay, so you heard the 8-year-old. Subscribe, like, and hit the notification button. Okay.
Yes. No, I've never.
Bell, sorry. Oh my God. Okay. So yeah, he's a YouTuber. He loves it. So let's see if there is anything from the audience. No. So what are your thoughts about academia? Let's discuss this a bit and then we will close the event. Academia and wanting to leave.
the one thing, I mean, one problem with academia is, of course, this insecurity of positions. You get 2 years, 2 years, 2 years, 2 years, always. And I know a lot of people that for that reason left academia, because they said, I cannot live forever in this situation. And one person ironically said, well, I shouldn't have a flat. I should have like a trailer or something that I'd always drive to the new place where my job is. And some people really then have a flat in one city where they live, at least in their mind, and then rent only a little thing wherever their work is, because they say every 2 years it changes. And I think that is a problem. Now, the other thing is, everything has two sides. I know also many people that left academia, and they said, and went to industry, and they said at the beginning they were great, but after 10 years they said they were frustrated because they were doing the whole day long something which they, in principle, they didn't want to do. And so everything has its two sides. So I know people in academia that were at the end very happy, but also unhappy ones. Other people in industry that were very happy, but also other people. And I know even several that went back from industry to academia because they said, I work in a company, but I can't do for the rest of the life doing exactly the same. And so I would say it's not easy. And then what I think is, really it is, if you find a position or not, is more related to luck or whatever than anything else, which is of course not very nice if you have no control on it. But I'm sure that it's largely just luck.
How about you, Sue? What are your thoughts?
I have a lot of thoughts about this. I think we should normalize leaving academia. Once you get into the higher education system, staying in academia is not the normal outcome, or should not be the normal outcome, or the extension of your life for the rest of your life. And leaving academia and finding a job and any company or in whatever industry should be a normal thing to do that people shouldn't look down on. But a couple of months ago I ran a Twitter poll asking people if they felt like people think they would fail or they had failed if they left academia, and many people do. I think this is a taboo, even like the way we talk about it, leaving academia, as if you're supposed to be a part of it for the rest of your life, is something that I do not agree with. I would like to stay as long as it makes me happy, and as long as I can find a job. But I don't think that's the end of the story. Many people who do not choose the path of higher education change jobs multiple times, or stay in one job. I mean, all paths are normal. And I think as a community, we should support people who want to leave. We should not, we should not say things like, well, they were so successful, why did they leave? They were doing so good in academia, and things like this that would discourage other people who are thinking about leaving. So
I don't think it's leaving. So this is what you say, we should normalize it. So we should stop saying leaving academia and say, okay, well, I worked here for a bit, and then I will work there for a bit, and I have all these skills and ideas that I can offer in another project or in another kind of job. But it's not only within the working environment, I think, this pressure, and this is why people feel like they're failing. It's within the family. So if the family thinks you are a failure because you are not going to be this professor, then it's a lot of burden. And it depends also, for example, you know, in Turkey and Greece and Southern European countries, family is very well connected. So there's a lot of pressure from the immediate environment of a person regarding this. They
Yes.
do consider you as a failure, and this follows you forever. And it adds up to all this stress about finding a job for the next path. And also, I think within academia, we don't train people, we don't prepare them for what they can do, what they can offer in other fields, you know?
Yeah.
So that's a big problem that we, as you know, current members of academia, let's say, we have to solve and make this a better place for everyone.
Yeah, I think also one psychological aspect of this whole thing is that we get so little time for ourselves because it's not a normal 9-to-5 job for many. Kudos to people who can maintain that lifestyle in academia, but I can't. We tend to define ourselves based on what we do, like as an astrophysicist. And once you leave astrophysics, how do you define yourself? And then you find yourself in this kind of a dilemma, you know, and think, who am I without what I do? And that should not be the default feeling, because you are who you are beyond your job, and changing your job does not change who you are. So
Ike?
I've two things to it. One is, I think last year, no, perhaps the year before, there was a series of talks in Jena about the change of the society. And that was mentioned that because of the technological evolution, they think that in the last 10 years, 60% of all jobs in Germany will disappear. Of course, not that 60% are then unemployed, but they will do something else. So what we think at the moment is typical for academia, that you change always, is something which will be soon to the whole society. And now one other remark, I'm from the north, from the very north of Germany. And in my school class, and in the north, you always keep the friends from school. It is that basically everybody from my school class goes to sea. And goes with a ship around the world, and that was the usual thing. And I'm a little bit exotic because I live in the middle of the country, and they always ask me, but there's no sea there. There are mountains and stuff. It's crazy. And for people going to sea, they have a life like this, because when you're on a ship, you're for several months on the ship. You go between Hamburg and whatever, Shanghai for a long time. And then after this, then they have like a month off or so, and they're at home, and they have really two different lives. And I thought academia is a little bit like being on a ship. On the ship, you can only do what you have to do on the ship. But then you think that then when you finish with this, you have a different life. And actually, these people that go to sea, I always think they have a tough thing, because for months they are only at the job, and they cannot go away. I mean, when you're on a ship, you cannot. I go out for a walk, impossible. They are on the ship. And that's actually what most of that's why I laughed a little when you asked, you want to go around the world. A lot of my classmates is what when they finished the school, they said, we want to see the world. And they hired on a ship and said, oh, let's go around the world a few times and see it.
The most difficult problem with academia, which you already mentioned,
Yes.
is the insecurity.
Exactly.
And it forces you not to have a private life, or your private life suffers a lot because of this insecurity of, you know, something permanent. So it would be amazing if you had a base, and then a permanent base, and then you could travel, get into that ship and go around the world. And that's amazing. And this is what, let's say, the previous generation was able to do, because after finishing their studies, they would get a permanent job and then they could do that. They're visiting scientists somewhere else around the world, but we don't have the luxury of doing that at the moment. And I mean, only last year, I sent 60 job applications to academia and another 60 to industry, and that's personal time above everything. So the system is broken, and you do have to be extremely lucky to get even one job in the 120. The odds are very, very small. So it's a very big problem, and we don't prepare people that are very well trained. They have fantastic skills, the things astronomers can do. It's like we cannot even describe them to an HR department, for example. But we don't prepare them for what they're gonna face out there, and this is the problem we have to solve. All of us together, not just one person. Anyway, sorry, I didn't want to end in a very dark note, so I will change the subject and have a question for both of you, and then
we'll but a positive one now.
Yeah, a positive, because we talked about life and different forms of life and exoplanets, and so my question is, if you could live in another planet and you could breathe the air and everything, where would you like to be? In another planet or in another body in the solar system?
Of course, everybody. No, it shouldn't be.
It's okay. Whoever has an answer first.
Yes. No. You first.
I mean, I've always dreamt of space travel, and I think people who know me, who are listening right now, could confirm that I have talked about being sent to Mars many times. This is something that I talk about very often, but I would love to be on Mars. In one of my scientific visits to JPL in California, I visited the Mars yard they created to train the duplicates of the Mars rovers. And I was just so fascinated by it. And I want to go to Mars. That would be my dream.
Amazing. Yes. I hope you get to go.
I honestly, if somebody at NASA is listening to this and you need diversity in your crew that you're sending to Mars, pick me.
You heard it, pick Sue, okay. And pick me too. I would like to travel also, but I would like also to come back. So it should be, a letter tour. And you, Ike, where would you like?
Actually, this is an almost usual question. In a galaxy 104, Messier 104, so in the center of Virgo cluster, because I was always thinking that must be an amazing place when you see out in the night sky and everything is not full of stars, but full of galaxies. And I thought that must be an amazing thing.
That is fascinating.
Now, one question related to it is also we are a little bit fantasy, which I discussed with a colleague. If you had the possibility to say fall asleep and wake up in 200 or 400 years, would you like this idea, yes or not? And with a colleague of mine, she said, no. In 400 years, I mean, everything is different. And I said, I would actually like to see how the world is in 400 years, because we have expectation of what's going to happen. And somehow one says, okay, one cannot live that long, but I would like to go to 400 years into the future. 400 years because languages are changing. And when you look back, and if it's longer than 400 years, then the people presumably speak a language which we cannot understand any longer.
Well, that's going to be very interesting for you, I think.
Yes, and so 400 years, that would be where the language has changed to whatever, but still you can say, okay, I can understand what the people are speaking. That's 400 years.
Fantastic. Well, guys, thank you very much.
I thought your answer. Would you like to go 400 years into the future? Yes, no.
Me?
Yes.
Huh. Yeah, okay. I like, adventures. Let's say, why not? I would also like this idea of being in the Virgo cluster and seeing other galaxies. I mean, I've never been to the south hemisphere, so I haven't seen with my eyes the Magellanic Clouds in the sky, which I really want to see. I've only seen the spiral arm of our galaxy in summer times. So I think being able to see something like that would be fascinating.
30 seconds to this, because that was my first impression when going to La Silla. We were picked up at the airport. It was night, and that was with my boss from London. He had also never been to the southern hemisphere. He looked out of the car and said, "Oh, weather is really bad. Here's a cloud, there's a cloud," and so on. Then we went up to La Silla, got out of the car, and then he thought, "Oh, these were the Magellanic Clouds." So you see them when you drive a car. And then the first one I was observing actually molecular clouds, with it where you sit in the dome, and I typed in the coordinates, and the telescope went to 1, and I thought, "Oh, you can see this." And then I typed the next one and moved to the next cloud, and I thought, "Oh, it's amazing, you see it."
That's amazing.
So southern hemisphere is so absolutely fantastic.
Yeah. Okay, we have a comment next for you. So that next time you should play something on the guitar.
Oh,
yes. You should play something on the guitar. That would be nice. Yes.
And I forgot when I was describing the love affair, the astronomical love affair, to show you this. I only described it. So I had a video. I can't believe I forgot. So look, okay, this is what I was describing, okay? This is the video from ESA. It's an artist's impression of what happens when a black hole in a system where you have a black hole and a companion star, so you have a stellar black hole, attracts the material from the companion star into this accretion disk, as we say, and then emits radiation also in the radio. So this is the impression of a micro quasar. And this is an artist's impression. So we have not observed this specific thing. It's an animation, okay? But it's very nice. And then, sorry for missing on that. I forgot I had it here. And then I want to draw your attention to how you can contact Astronomy on Tap Jena. So you can contact me everywhere, basically. On Gmail, aotjena@gmail.com. On Facebook, you can follow on Twitter, Instagram, of course, YouTube. At some point, there used to be a TikTok, or maybe there will be a TikTok in the future. We will see if I have time. But yeah, so if you have questions or you want to discuss more, don't hesitate. I'm always happy to answer your questions. And if you have more questions for our guests today, feel free to answer under the chat, even when the live is over. You can ask questions and we will answer to you guys. Right, so it's past 9 and I will end this now because it's been a long one, but thank you so much. I had such a good time having you here, learning about your career paths and how it drove you to do astronomy and all the fascinating things you do. Thanks very much for the interesting talks. And thanks to the audience. You've been great. And guys, we will see you next time, March, in a month. Okay. Good night.
Good night.